Okay, well, let's get started to keep things on track here. We've got about 30 minutes. My name is Steve Sabin. I work for Bruel Kjaer Vibro, and we're going to take about 30 minutes. You might have heard my boss, Randy Chitwood, talk a little bit about what we do with vibration data this morning during the keynote. And what I would like to do for the next 30 minutes is demystify how do we do that? How do we put vibration data into the PI system? So here's a little bit about us. So SETPOINT is the name of the product, and you can actually see it in our little kiosk out in the expo. The name of the company is Bruel Kjaer Vibro, and we were recently acquired by Bruel Kjaer. They're based in Darmstadt, Germany. SETPOINT operations are actually in a pretty beautiful spot near Lake Tahoe in Nevada. So there is where we're located, that little red dot. We're about 30-minute drive from the shore of Lake Tahoe. We make two products that are part of the Bruel Kjaer family. One of them is a machine protection system. For those of you who are familiar with API, the American Petroleum Institute, this system is conformed to API 670. And we also make condition monitoring software. And a lot of what we'll be talking about over the next few minutes is the condition monitoring software, why we chose the PI system, how it works with the PI system, how we get the data into the PI system. So why would you do this? Why would you want to put your vibration data into PI? And the answer is very simple. Because every system in the world that does vibration data uses a proprietary silo like we pictured here. And what we've done is we've essentially gotten rid of that and said you don't need it anymore. You can take the data that you would have put in this proprietary silo and you can get rid of it. You can get rid of the silo, you can stream that data directly into the PI system. Now usually what happens is IT people, instrument and control people, automation people, they're completely on board with this approach. They like it because it eliminates infrastructure. Where you tend to run into the skeptics is with your rotating machinery people, because they've been trained for their entire career that you cannot put this kind of data into an operational data historian. It's not fast enough, it takes too much bandwidth, it will require too much storage. And so what we do is we educate people, is we show them how do we do this in a manner that won't break your PI system, it won't rob your machinery people of the data and the capabilities that they're used to getting through a standalone system, and it's actually better. And one of the reasons it's better is because all the data that they typically need to solve a problem with machinery is not only located in this vibration silo, but it's also here, it's in the PI system. All the process data about what's happening around the machine, they need to put those two pieces of data together, the process and the vibration data. And when they are in the same system of record, as OSI likes to say, you have one version of the truth. When you put those together in one place, it's much easier for machinery engineers to do their job because the process data, the vibration data is all together in one place. So how do we put waveforms in PI? Well, let's take a look at some time series data. I'm not going to tell you what this is. I'm simply going to tell you that it's time series data. Now, if my delta t is long enough, let's say an hour between my data points, how many people think I can put data like this into a PI system? So if I tell you this is 27 Celsius and this is 14 Celsius, and this data occurred around high noon, and this data occurred sometime around 1, 2 in the morning, you would say, oh, well, that's a sinusoid of daily outdoor temperature. I can easily put that into a PI system. Where people's head explodes is when you tell them vibration data is the same. It's no different. And generally they won't believe you because they've been taught their entire career that vibration data is special and vibration data is different. But conceptually, take a look at what we do here. All we do is we change delta t. We make it 1 millisecond, for example. So now my data points aren't an hour apart, they're a millisecond apart. And I change my vertical axis. Now I'm not talking about temperature, I'm talking about displacement from a vibration probe. So I might have a peak at 4.2 mils. A few milliseconds later, the waveform goes through a trough, 0.9 mils. Now what do I have here? I have a vibration waveform. It's just time series data. I can put that into a PI server because that's what a PI server is good at, is time series data. PI can resolve time down to 15 microseconds. And it turns out that that is really the key for doing vibration data, is if we can line things up properly in time, if we can resolve time accurately, then it allows us to do all the things we need to in the vibration world. So that means if we can timestamp the data, then we can move entire blocks of data into a PI system, which is what we've depicted here. So it's no longer temperature data with an hour between the data points, it's vibration data with milliseconds between the points. And because PI can resolve time so incredibly well, it allows us to take, say, 3 vibration probes, a phase probe, an X probe, and a Y probe, line them all up in time, and do things like draw a shaft orbit. So the system works very, very well. As you may have heard this morning, the time from when we started this journey with PI to where we actually were able to do this in a PI system took only about 6 weeks, and within 6 months we were shipping a product to customers. If we were to take all the data that a vibration sensor can produce and send it all into PI, we would probably be, a typical machine has about 20 vibration sensors. And if we do the math, the bandwidth of vibration data is roughly equivalent to the audio spectrum, 0 to 20 kilohertz. So if we were to take all of that data from a single sensor and stream it into PI continuously, and we did that for a whole machine, 20 sensors worth, we would consume about 1 terabyte a week in a PI server. And of course, nobody is going to be too happy about that. So one of the reasons that our device is considered an edge device is because we have to intelligently decide what vibration data are we going to send to the PI server, and what data do we not have to send because it's not interesting. So here we have the way that data is typically provided. So what you're looking at on the red curve is a machine startup profile as the RPMs change. We can do what's called delta time, where we have evenly spaced samples in time, and we can send those to PI. We can do what's called delta RPM, where now the time axis, the data is unevenly spaced, but it's evenly spaced along the RPM axis. And we can write that data into PI. That's called delta RPM data. Competing systems basically have only one other mechanism by which they can store data, and that's called an alarm buffer. In theory, an alarm buffer sounds like a great idea, and it looks like this. Here's a bar graph. This is what operators would see. Pardon me. And let's say that we move forward in time about 25 minutes. Now our vibration has more than doubled. Operators would be very interested in that blue trend because it was such a dramatic increase. But what happens in most systems is all they will really do is store a little bit of data before an alarm and after alarm. So here we'll move forward 9 more minutes, and then during this last 60 seconds, our vibration level will creep upward until we get to this alarm threshold. Boom. And what you would find in other systems is they keep what's called an alarm buffer. So we would get some data before this alarm. We'd get a little bit of data after the alarm. But if you're a machinery engineer, the vibration in that green region and in that yellow region, it's not really that interesting. What you would actually like to see is the vibration that's occurring down in this blue region when you had such dramatic changes. So the way that we've engineered our edge device to handle this situation is we're constantly looking at the vibration, and we're asking a very simple question: did it change? If it changes, we send it to the Pi server. If it doesn't change, there's no reason to send it to Pi. This is exactly how video works when you stream video. If you think of, say, a frame in a picture that has a lot of blue sky, and maybe there's some green grass, and there's a person in that image who's moving. Maybe they're talking, maybe they're waving their hand. As we send one video frame and then the next video frame and the next, we don't have to send the pixels that aren't changing. We don't have to send the pixels from the blue sky. We send the pixels from the part of the screen or the part of the frame that's changing. And we use the same ideas here in terms of vibration. And the way that we do that is we look at the vibration waveform. So our edge device brings this in, samples the data, and then it examines the vibration waveform along essentially 4 different criteria, or 4 axes. So we'd look at amplitude of the vibration, we'd look at the period of the vibration, the speed of the machine if it's changing. We look at what's called the bias or the gap voltage if that's changing from the sensor. And then we look at the frequency content. If none of those are changing, then we can say for all practical purposes, the waveform itself hasn't changed. And this is basically the intellectual property that's embedded in the edge device that allows us to decide when do we need to send waveforms to Pi and when do we not have to send waveforms to Pi. So what does this look like in practice? Well, here what we have is a machine speed. That's what we call slow roll, and then we ramp the machine up. It levels off, and then we ramp the machine back down. And these little tick marks that you see here are waveforms. So essentially, all through here, because nothing interesting was happening, we didn't have to send any data to the Pi system in terms of waveforms, because nothing interesting was happening. The waveform, for all purposes and intents, right here, was the same as the waveform here and all the way through here. But notice, as I start to ramp the machine speed up, here's my vibration amplitude. It runs through a resonance and a second critical speed. So my machine is changing, and it's very interesting. The speed is changing, the vibration amplitude is changing, the vibration frequencies are changing. And so the system recognizes that, and all these little tick marks that you see are waveforms. So the system is basically storing waveforms because it needs that data to characterize what's happening in the machine. Down here, it didn't have to do any of that. In fact, all you see right here is one little set of tick marks because the system had been configured to save a waveform every 20 minutes, whether conditions were changing or not. And it had also been configured to save waveforms in this region because things were changing and things were interesting. So a good way to think of what our edge device does, what our box does, is it is looking at, is the data interesting? And you get to define, you can configure what is interesting and what isn't interesting. Our speed change is interesting, our amplitude change is interesting, and so forth. Now I'd like you to take a look here. We have our cursor, and it's showing what the waveforms look like right at this moment in time. And now I'd like to move my cursor down here, right over here. I've got what a lot of people in the machinery world would call a bump in the night. So I move my cursor down here, and I can zoom in a little bit. See this little bump well below my alarm limits. What I want to happen in a system like this is when something interesting occurs, I want it to capture that. And I don't want it to necessarily have to exceed any kind of alarm threshold. And as I explained earlier, we look at the waveform and we ask a very simple question: did it change? And when it changes, we save it. When it doesn't change, we don't have to save it, because the waveform right now is like the waveform from a few seconds ago and a few seconds before that. So what you see here is the system, when it saw this little excursion, it saved waveforms. And that's exactly what we see here in these plots. I can go backwards a minute, and I can see that a little bit better here. So these waveforms are obviously very different than these waveforms. And the system automatically detected that, automatically sent it to the Pi server. So how do we visualize this data? So it's fine that we can put it into a Pi server, but Pi doesn't know how to visualize most kinds of vibration data. You know, it can visualize trends. So this is a process book screen, for example, that one of our customers in the Houston ship channel at a refinery built. And he made a machine mimic diagram, and he made little bar graphs to show current values and alarm statuses and trends. And his philosophy with this process book was he wanted to come in every morning, get his cup of coffee, take a look at his dashboard, and if he didn't see any trends or alarms or anything, he'd just move on. And he wouldn't look at these screens till the next day or unless an alarm occurred. But if he saw something interesting, he wanted to be able to click on a bearing and drill down and take a look at the vibration data. Now, he can't do that from the normal Pi visualization tools like Process Book and Pi Vision. But we make what amounts to a free viewer, kind of like Adobe Acrobat Reader, that you can download from our website, and it looks like this. And this is the software that allows you to visualize that vibration data that's in your Pi server. So the shaft orbit, the shaft vibration waveforms, the FFT data, so now we can see the data in the frequency domain. This is known as a polar plot. It shows us how the vibration amplitude and phase changes as we go through the speed. And what we're looking at here is a machine that ramped down, ran through its second critical, ran through its first critical, and then went into slow roll. And this is a real machine. This is a GE LM6000 gas turbine in New Zealand. I personally went to the customer site to collect this data. And what you're seeing down here in the time slider, it's a peaking unit. So about 6 in the morning, they brought the unit up. They ran it for about 3 hours to meet the morning electricity demands. And then they coasted the machine back down and turned it off until the evening when they needed it again. So this visualization software is because, again, not because the data is stored some different place. It's all in Pi. But Pi doesn't know how to visualize these specialized plots. These are the things that rotating machinery engineers like to look at. These are the things that vibration analysts need to look at. They can't do it in the native Pi visualization tools, and so we just built a special viewer that allows them to do that. So what kind of hardware do you need to do what I've just described? Let's say you already have a permanent vibration monitor. In this case, we've depicted one from GE, Bentley, Nevada. You can take the SETPOINT hardware and you can literally put it on top of your existing protection systems, stream the data out of that underlying protection system, and once we've digitized it in the SETPOINT hardware, we can stream it into your Pi server, and once it's in Pi, then you can visualize it. So we would call this augmenting your existing installation. The other thing you can do is you can use SETPOINT technology to replace your existing vibration system. So let's say what we've shown here is a monitoring system that was introduced in about 1988, so it's 30 years old. Most customers would be interested in replacing that if it was in their plant. And we do quite a bit of this actually as a business. And in this instance, we would take that system out, so rather than augmenting it, we'd replace it. And we would put a SETPOINT rack in its place. And then that SETPOINT rack could do all the things that we described. It could stream the data into your Pi server. And then once it's in Pi, you can visualize it. Now, one of the things that we've done in this device is we've put an enormous amount of onboard memory. It works like a flight recorder. We can store 1 year of data in that box for 56 vibration channels. And what that means is that if I were to ever lose my connection to Pi momentarily or for a day or an hour or a week, I would not lose anything because it's stored in my edge device. When that connection to the Pi server is restored, it just makes it up. It just backfills the data into Pi. Or let's say I have a very low bandwidth connection here. I'm on an offshore platform, my Pi server is on land, and I don't have a real high-speed network. That's okay because this will buffer, as I said, about a year's worth of data, and it will just trickle it out over a low bandwidth connection to the Pi server. So you don't have to worry about losing data just because your network goes down or your Pi server. Many times the Pi server, of course, is high availability. It's very reliable, but the networks themselves may not be. And so this is how we deal with that situation of a poor network connection or a problem. So who's using this system? Well, as you saw this morning, or perhaps you missed the keynote speech, but one of our customers here in Europe is BASF at their Ludwigshafen facility, which I think, if I'm not mistaken, is the world's largest chemical complex. So I'll just play that video again, and you can hear BASF talk about why they were so intrigued by this and some of the problems it solved for them.
BASF Rotating Equipment Department started 2013 and market research for a new machinery protection and contagion monitoring system. SETPOINT and some other manufacturers met the most of the BASF requirements. And the most important benefit of the SETPOINT system was to use infrastructure, the customer side, to stream vibration data directly from protection monitoring system to a Pi system.
The solution gave us the opportunity to link field data directly into our Pi server.
Now we are able to put all relevant data to one diagram. Not only vibration data in this database, we have also process control data with the same time step.
Gave us the opportunity to reduce hardware in the field. We don't have any in-field analysis units anymore, which can fail or have to be replaced regularly.
You're also able to store waveforms.
The administration comes down to a single server, so we don't have to administer like 30 or 40 different computers in field. We just added another functionality to our existing Pi server.
At the beginning we have been a little bit skeptical because it's known that a fast-starting machine can produce a lot of data in a short time. But after some tests we have seen it really works.
We have online data access in our whole corporate network, so we can access the data where we are and when we want it.
Not only static data like vibration or speed trend can be saved, but also high-frequency sampled data like orbit or FFT spectrum.
Now we have an architecture which is very flexible and expandable.
Paul was the first fellow you saw in the video with the lighter colored hair. And Paul actually came from a background where he had worked with a separate vibration system. And he's the rotating machinery guy. And as I mentioned earlier, these are the people that are skeptical. They've been taught their entire career that you can't do this in a Pi system. And if you try to do it in Pi, you're going to have to sacrifice a lot of the functionality. You're going to basically be downgrading yourself as a machinery engineer because you won't have the tools to do your job. And he mentioned, there was a word in there, he said, we were skeptical. And it's true, we run into this all the time. The machinery engineers are skeptical. And so often what we have to do is demonstrate. We'll go put a SETPOINT rack in. We'll stream data into Pi and we'll let them see for themselves that it can do the things that we talk about. And so Paul really had this aha moment of, this really works. Wow, this means we can tear out all of this other software that we have to pay quite a bit of money for every year in terms of service contracts and things. And we can do this in our Pi system. BASF is an EA customer, which means they don't have to go buy any more Pi. Every time they want more tags, they want more servers, they need different interfaces, they've already bought it. And so this is one of the real benefits to Pi customers, and particularly EA customers, is you already own the software to do this condition monitoring and this vibration monitoring, and a lot of customers don't know that. They don't understand that their Pi system can be used in this fashion. So BASF, pardon me, did this. They were able to take out infrastructure, other software, other servers and so forth, and just do it all in their Pi system. Maximilian, the second fellow that you saw in the video, he's really more on the Pi side. Paul's on the rotating machinery side. Maximilian was on the Pi side. And what he liked about the system, of course, is now he doesn't have 30 or 40 servers spread throughout BASF's facility. He just uses the big Pi server that they have. He only has one environment that he has to administrate and so forth. So this solution works extremely well for anybody, whether they're Pi users or not, because we do have customers that aren't Pi users, and we simply embed Pi and we deliver them a standalone vibration system. But for people that are Pi users, it's incredibly powerful because they already have their process data in Pi. Now they put their vibration data in Pi. We bring those two worlds together for them. They can literally get rid of the old third-party software that they might be using and just use their Pi system instead. So this morning you heard again from my boss, Randy Chitwood, during the keynote. I'm the guy on the bottom, Steve Sabin. If you'd like to know more about this than we're even able to cover here, I invite you to stop by. We have a little kiosk out in the expo area, and we'd be happy to talk to you and answer any questions you have about this technology. Now, I think we're down to T-minus 2 minutes here, so I'll take any questions that you might have. Yes? Not yet, but Bruel Kjaer is very strong. We are actually the world's leader in monitoring wind turbines. So we have hardware that goes up in the nacelle on wind turbines. We've sold about 17,000 of those systems over the last 10 years. And one of the things you're going to see us do in the next 18 to 24 months is to take that hardware that goes up in the wind turbines and engineer an interface so we can get that data into Pi, just like the SETPOINT system we've shown here.
Thank you.
Excuse me. Is it possible to upgrade Vibro Control 1000 to use the system?
The VC1000 is a pretty old piece of hardware, as you know. It's kind of a brick. And we can certainly take that out and leave the sensors that you have, so you wouldn't have to exchange the sensors, but we could replace, say, a VC1000 with the SETPOINT technology, and then we could do the things that you saw here. So we'd have to replace it. We couldn't really upgrade it, but you could keep the sensors. Yes? Okay, any more questions? Okay, I think we did a pretty good job on timekeeping. I see 11 seconds left on the clock. So thank you. I'm just gratified to see this much interest in vibration monitoring, and if you'd like to know more, as I said, just stop by our kiosk. Thank you.